Okay, let's look at the properties of electric lines of forces, which is very important. Since we know charges are having electric field, right? These are imaginary. In order to represent the electric field, we represent it by certain lines. We call it as electric field lines. Okay. What are the properties of electric lines of forces? Okay, the first property is they are continuous with no breaks. These electric field lines are always continuous and doesn't break. Second one is they start from the positive charge and ends on the negative charges. Okay, let's consider the positive charges. For the positive charges, we are drawing the electric field lines always in the outward direction. In the outward direction, we draw the electric field lines for positive charges. And in case of negative charges, we draw the electric field lines inwards. Okay. So what happens is they always starts from the positive charge and end up on the negative charge. Okay. The third point is, and also you have to know that they do not form closed loop. Even though they start from the positive and end up on the negative, they don't think like they form a closed loop. They do not form any closed loop. We'll discuss why they do not form any closed loop. Okay. The third point is the tangent to the electric field lines drawn gives the direction of electric field at that point. That means if you draw the tangent tangent of the electric field lines, the tangent gives the electric field direction. Okay, what was the first point? These electric field of lines are continuous with the no breaks and always starts from the positive and end up on the negative, and they do not form any closed loops. And also the tangent gives the electric field direction. Okay, and also they do not cross each other. These they do not cross each other means they will not intersect. If they intersect, what happens is, if they intersect, we can draw two tangents at a point. Two tangent means for a single charge we are getting two electric field lines. So not two electric field lines, two directions. At a point, electric field will be having only one direction. If they intersect, what happens? If they intersect, we'll get two tangents. We can draw two tangents, right? If you are able to draw two tangents, that means you are able to getting two directions, which is not possible. So we always say that they do not cross each other. Get my point? They do not intersect each other. If they intersect, what happens? If they intersect, which is not possible, if they intersect, what happens? We can draw two tangents which gives two directions, which is not possible. Okay, then the direction is always normal to the surface. Electric field lines direction is normal means it is always perpendicular to the surface. Always you have to remember this one. The electric field lines are always normal to the surface. Normal means perpendicular to the surface. Then equidistant means uniform electric field. That means if the electric field is uniform, what we see is equidistant electric field lines. Equidistance, that means after a certain distance electric field lines like this, then the next lines will be in the similar regular distance. Regular distance if it keeps a regular distance or equidistance, then the field will be uniform. If we having different separation, that means non-uniform field. You have to remember all these points from 1 to 6. Look at these figures. You'll get positive charges, the electric field lines are always outwards, and negative charges it will be inwards. And positive and negative charges, you look at this, they will attract the field lines. You look at like they are attracting. If they are the similar charges, they will repel. Okay, you got the point for properties of electric field lines of force. Okay, you understand that? Okay, then now we are going to move on the electric field. Already we have discussed the electric field. Now we are going to move the electric field for a point charge. Okay. Okay, next we are going to learn the electric field due to a point charge. Okay, that means in our section, in our electrostatic section, we have discussed about charge. Our hero was charge, right? Then we talk about our hero, that means our charge, what was the basic properties of charges. Okay, how we get the, how we form these, how to make a material charge. Okay, then we move on to the Coulomb's law, forces of interaction. Then we have already discussed about electric field. What was electric field? In our part 1, part 2 videos of the electrostatics, we have discussed electric field. Electric field was, yes, the space around a charge in which a test charge, a unit test charge experiences a force. Those areas, those regions we call it as electric field. What was electric field? It is a space around a charge in which a test charge experiences a force. A test charge. Test charge means we are considering the test charge as a positive charge which experiences a force. Okay. Now we are going to find the electric field due to a point charge. Let's consider a point charge Q. Let's consider a point charge Q. This is our point charge. Okay. This is our point charge, and we are going to find the electric field of this point charge at a certain point over here. I'm going to find the electric field of this charge at this point P. In order to find the electric field for this charge at this point, what was electric field? What was electric field? What was the definition? According to the definition, it says that electric field is the force experienced by a test charge. You have to experience, if there is an electric field over here, since there is an electric field at these points due to this charge, how will you recognize whether there is an electric field is here? You have to use a test charge. That means the force acting, how much force is acting on the test charge. I am considering Q naught as the test charge. This is our test charge. Okay, this is our test charge. So I am bringing the test charge from infinity. Infinity means, basically it says that from a far point. That means from a far point I am bringing a test charge. I am bringing a test charge towards this point P. Okay, towards this point P I am bringing a test charge, which is the Q naught. I am bringing this Q naught to here, this point. Okay. Yes, that means this Q naught experiences a force. This Q naught experiences a force at here due to this charge. Okay. So in order to find the electric field, we need force also, and also we need the test charge. What was the force? That means the force between this charge and this Q naught. When it comes here, there will be a force of attraction or repulsion between these two charges, right? So what will be the force? What will be the force? What will be the force? F. F you can write it using the Coulomb's law. That is, F is equal to 1 by 4 pi epsilon 0 Q, then Q naught, divided by, let's consider the distance. Let's consider the distance from here to here is R. That means square of the distance, that will be R square. If you write it in the vector form, that will be R cap direction. This direction will be R cap. Okay. That means electric field, you can write it like electric field is equal to F by Q naught, which is equal to 1 by 4 pi epsilon 0 Q naught by R square vector R cap divided by Q naught, right? You can cancel this Q naught and this Q naught, and you can write it like electric field is equal to 1 by 4 pi epsilon 0 Q by R square R cap. Okay. This is the expression for electric field due to a point charge. This is the expression for electric field due to a point charge. Okay. What is the expression for electric field due to a point charge? How will you determine this? First of all, you have to consider a charge Q. You have to find an electric field at a point P. In order to find, before finding this electric field, you have to confirm there is an electric field. How will you confirm it? You can test it by taking a test charge from infinity to that point. We know electric field is equal to F by Q naught, that is force per charge. Force per charge is our test charge. Force you can determine using the Coulomb's law, that is 1 by 4 pi epsilon 0 Q naught by R square times R cap. R cap is the unit vector. Then you got the force, you also know the test charge, substitute over electric field is equal to F by Q naught, right? Electric field is equal to vector F by Q naught. That means you can cancel Q naught, and finally you will get the electric field equation is equal to 1 by 4 pi epsilon 0 Q by R square R cap. Okay, got it? This is electric field due to a point charge. Next we move on to the charge distributions. Charge distributions. Okay. Okay, now we have learned the electric field due to a point charge, a single charge. Okay, let's look on to two charges.